Assalamualaikum warahmatullahi wabarakatuh and very good morning. Today we will be presenting about resistance report and ship development in Mexico for advanced naval architecture. Our group consists of Nur Hadilah Shahada binti Muhammad Iwan Idham, Nur Atika binti Nawar Ashraf, Hashimiyana Putri Faminito, Nur Izzati binti Muhammad Singh, and me, Aisha Mohammed binti Muhammad Rudzi. The agendas of this presentation are introduction, literature review, objectives, methodology, result, discussion, and lastly, conclusion. Introduction. Ship resistance to total force opposing a vessel's motion through water is a key concern in naval architecture and compromises components like wave making, frictional, air, eddy, and foam resistance. Accurate estimation of these forces is essential for determining propulsion power, improving fuel efficiency, and optimizing vessel performance. Tools like MySurf aid in minimizing resistance through hull design. The ITTC 1978 guidelines, developed by the International Towing Tank Conference, provide standardized methods for model testing and scaling results to full-size ships, incorporating form factor, wave making, and frictional resistance. Resistance tests involve towing ship models and applying Fruit's hypothesis, which separates cell resistance into viscous, linked to flat plate friction, and wave components, enabling reliable predictions and efficient ship design. Literature review. The evolution of ship design has been closely tied to understanding and reducing hydrodynamic resistance. Modern tools like MaxSurf have revolutionized this process by replacing traditional towing time tests and empirical methods with advanced computational simulations. MaxSurf supports resistance prediction through empirical ultrabalance, Savinsky, numerical potential flow panel methods, and hybrid techniques. It enables detailed hull form optimization using surface modeling and parametric design, with validation through comparison with experimental data. The software enhances ship performance, fuel efficiency, and compliance with IMO standards, making it essential in developing innovative, sustainable, and cost-effective vessels. Derivation of form factor. Form factor accounts for the influence of hull shape on viscous resistance. It is derived by separating total resistance CT into frictional CF, viscous, and wave components. Three main methods to find 1 plus K are 1. Low speed testing where wave resistance CW is almost to zero. So 1 plus K is equals to CT over CF. Next is the Prohaska method, which is to plot CT over CF versus root number to the power of 4 over CF and find the intercept, which is 1 plus K. And lastly is the direct measurements of viscous and wave drag to isolate form factor. ITTC 1978 Performance Prediction Method. This method revolves around predicting full-scale resistance using model test results and correction terms, which is this formula CTS equals to 1 plus K times CFS plus delta CF plus CA plus CR plus CAAS. Delta CF is roughness allowance, CA equals to correlation allowance, CAAS is the air resistance. This method uses standard values. Example, Ks equals to 150 times 10 to the power of negative 6 meter. CDA is almost to 0.8 if no data is available. Ensures consistent extrapolation from model to full scale using void similarity and empiric adjustments.
The first objective is about to carry out resistance prediction using method testing for a 181.5 meter bulk carrier in calm water condition. Second is about to predict total resistance of the ship using ITTC 1978 performance prediction method to given bulk carrier particular as shown in figure 1. This figure shows 181.5 meter bulk carrier. The bulk carrier particular with respect to the actual full-scale test condition are listed as below. Length overall is around 181.5 meter. Length between perpendicular 172 meter, LWL 175 meter, breadth 30.5, depth 16.4, graph 11.373, displacement about 50303 tons, and the black coefficient is about 0.85. The next objective are to present the result of the total resistance and the effective power for the bulk carrier, including the form factor prediction using Broha plot. And the last is to compare the resistance and the powering result from exploration model test and prediction method, which is never cat or massive. For the methodology, the first one is by using MS Excel program for the manual calculation, and the next is we are going to use towing tank and 180.5 meter bulk carrier scale model as shown in the figure 2. For the apparatus part, the first one we are going to use MTC hull model. Second is using towing tank. Third, by using a ballast weight. Fourth, swinging frame. 5, DAAS, and also by using towing carriage. For the model scales, for scale ratio for the ship is 50 and model is 1. LOA for the ship is 181.5 and for the model is 3.63. For LBP is 172 and for the model is 3.44. For the beam ship is about 30.50 and the models is 0.55 and draft mean for the ship is 11.373, but for the model is 0.45. For LCB from FP for the ship is 90, and for the model is 1.54, and the kg from baseline for the ship is 5.5, but for the model is 1.8. Weighted surface area for the ship is 73 to 7.775, but for the model is 3.5.
The graph clearly shows a declining trend in the relationship between the Reynolds number and the frictional resistance coefficient. The CF value continuously falls as the Reynolds number rises, suggesting that at greater flow velocities, the frictional resistance per unit surface area decreases. This is to be expected as more turbulent flow, which is usually caused by higher Reynolds number, lessens the impact of vicious effect in comparison in initial forces. When extrapolating model scale results to full-scale ship performance, it is important to take this variation into consideration, particularly when estimating total resistance without taking air resistance (CAA) into account. The observed trend supports the use of ITTC 1978 friction line in resistance prediction. The graph shows that the residuary resistance coefficient remains relatively low and stable at lower Reynolds number, but begins to rise sharply once the Reynolds number exceeds approximately 8 times 10 to the power of 10. These critical results demonstrate that at higher velocities and thus higher RNs, wave making and vicious effects become much more significant, causing CRs to increase rapidly. This trend directly supports the research hypothesis. As ship speed rises, the influence of residuary primary wave resistance becomes much more pronounced compared to frictional resistance, which aligns with the ITTC 1978 method's prediction and highlights the need to minimize residuary resistance in efficient ship design at higher speeds. The graph clearly shows a declining trend in the relationship between the Reynolds number and the frictional resistance coefficient. At greater flow velocities, frictional resistance becomes less significant, as evidenced by the steady drop in CFs as RNs increases. This behavior is consistent with theory, which states that as Reynolds number rises, turbulent boundary layers decrease frictional drag per unit area. This tendency is crucial for correctly projecting model-scale frictional resistance to full-scale shapes. This must be carefully adjusted to prevent performance forecasts from underestimating the total shape resistance. The graph shows that the effective power needed grows sharply and non-linearly as ship speed increases, particularly over 12 knots. This crucial finding reveals a cubic-like connection in which the power requirement more than doubles, which is from about 500 to over 6,000 units, when ship speed is doubled. The research hypothesis is that greater ship speed significantly increased propulsion power needs due to increasing hydrodynamic resistance is directly supported by this sharp rise in necessary power, highlighting the significance of choosing the right speed for ship design or operation.
Next, for the discussion, we have three main topics for the discussion. So the first is resistance analysis approach. So this study is actually applied a Maxwell resistance module to evaluate the total ship resistance across different speeds. So while the actual towing tank results are pending, so the setup and scaling module provide a theoretical foundation for understanding. Second is the design principles and software use. So Maxwell proved to be a powerful tool in estimating hydrodynamic performance in early design phases. Thirdly is the effect of hull shape on resistance. So the model scale and form factor calculation suggested that finer bowels and streamlined forms would likely result in reduced wave mixing resistance. And lastly, for the conclusion, the preliminary ship design and resistance analysis conducted using methods. So this provided a valuable insights into hull performances. So the application of theoretical scaling and form factor derived aligns with established naval architecture principles. So although experimental resistance data are yet to be obtained, the current computational modeling and systematic approach lay, say, lay a solid foundation for future validations. So therefore, work will involve towing tank experiments to verify and refine resistance prediction from Maxwell simulations. So overall, this project highlights the efficiency of integrating computational tools in early stage ship design and performance evaluation. That's all from us. Thank you very much.